Swayam Prabha. Digital India. Educated India.
Hello and welcome to lecture number 16 of the course Robot Motion Planning. In the last class, we looked at basic search algorithms. That is, when you have multiple paths which are possible from the initial point to the goal point, avoiding obstacles, which path are you going to take? Now, when we are saying the best path, it could be best in terms of the shortest length, or it could be best in terms of least energy consumed, or it could have some other cost function in terms of optimality. Now, some assumptions that we have made so far is that one is that the robot is a point robot. So when we are doing path planning in C-space, the robot is a point robot, okay? And it can move in any direction. Now you know that in the real world, the robot may not be able to move in any direction. And that means there are some constraints or kinematic constraints to its motion. For example, a car that you see, automobile in the road, it can go forward, it can turn at a particular angle, but it cannot go sideways. Now, not being able to go sideways is because of a kinematic constraint, a non-holonomic constraint there. Okay, so today what we'll look at is when we are going to the real world and there are robots which have kinematic constraints, then how do you do the path planning? Okay, so today's topic is path planning or motion planning with kinematic constraints. Okay, so today we'll be talking about motion planning with kinematic constraints. Now, kinematic constraints basically means there are some constraints to motion or to moving in a particular direction. Now, just very quickly explaining what I'm talking about here is that when we talked about other methods like visibility graph, for example, or the potential field method. In visibility graph, we have obstacles, and then we have an initial start point. Let's say this is my initial point, this is my goal point. And what we do is we connect each of the vertices by straight lines. Okay, so whichever vertex is visible from one vertex, we just connect it by straight lines and then try and see how can I go from the initial point to the goal point. So in this particular case, for example, this could be a path like this. Okay, that could be a path. Okay, that will take me from the initial point to the goal point. In potential field method, we saw that we have obstacles. For example, this is an obstacle, and these are plus repulsive field is there on the obstacle, and this is my goal, which has an attractive field, let's say minus, and the robot has plus. This is my robot, and what we have seen is that the robot is attracted towards the goal, repelled from the obstacle, and as a result it goes to the goal. Okay, so at every point in the vector field, the robot is subjected to a repulsive field and an attractive field, because of which the robot finally goes to the goal point. Okay, now here also we are making the assumption, number one, is that the robot is a point. Okay. Now, the second thing that we are making, the second assumption that we are making is that the robot can move in any direction. Now, I'm sure you are aware that the robot, and many of the robots, like mobile robots, cars, they cannot move in different directions at the same time, especially they cannot move sideways. Okay. Now, there are robots which can move in any direction, which are holonomic robots. But there are also robots which cannot move in all directions, which are non-holonomic robots. Okay. So, for example, a car can go straight and it can turn, but it cannot go sideways. Okay. So, today we'll be looking at path planning and especially whether it is possible to take this kind of non-holonomic robots and position them wherever you want. And that is what we talk about in terms of controllability. So, these are some examples. So, the assumptions is that robot can rotate and translate in any direction. Okay, so this is an assumption, and planning has been done using a point robot, assuming that the robot can rotate and translate in any direction. But these are some examples of robots. For example, this humanoid robot. Okay, now it can rotate, it can translate and rotate in any direction. Okay, this humanoid robot can rotate and translate, whereas this robot which is here, which is mounted on wheels, for example, you look at this one on the right side, this is mounted on wheels there. Okay, now this robot can go front, it can go front, okay, it can turn at a particular angle, but it cannot go sideways. It cannot go sideways like that. Okay, so suppose I draw the top view of this robot. So this is my top view. There are two side wheels on the sides. These are the two wheels. So this robot can go straight. So it can go straight, it can go back, it can turn at a particular angle. Okay, but it may not be able to go sideways. It cannot go sideways. It can rotate at an angle, it can rotate at this point, but it cannot go sideways like that. Okay, now in such cases, or in such cases where there are kinematic constraints, then we'll see how we do the path planning for such robots and such systems. Okay, so this is an example. There are many examples. The other example is that of a car. So we have a four-wheel car or an automobile that we see in the car in the roads. So this has got a steering in front. Okay, so there is a steering in front. So this car can go front. It can turn at a particular angle. Let's say it can turn like this or turn like this. It can go back. Okay, but it cannot go sideways. Okay, so such systems are basically called non-holonomic systems. And they are non-holonomic because they are subjected to a non-integrable kinematic constraint. Okay, now there are robots which can go in all directions. For example, this is an omnidirectional mobile robot, which is called a holonomic mobile robot. If you look at the wheels of this robot, these are what are called magnum wheels. And if I just draw the enlarged view, so this is a wheel, and on the wheel there are rollers. You can see these rollers. Okay, so these are rollers which are mounted at an angle to the axis of the wheel. So these are rollers like this. Okay, there's a roller here, there's another roller here, okay, maybe another roller here. Okay, now what happens here is that because the rollers are having an angle to the main axis, this is my forward direction, there is a resultant force which is in this direction, F. Okay, so when this when the wheel is rotating, the robot is subjected to a force which is not straight front or back, but has an angle to the axis, to the forward axis. Okay, because of which the robot can move in any direction. So now if you have a robot like this, as shown here, and there are four wheels, 1, 2, 3, 4. So if I draw the top view, it will be something like this. Okay, and we said that this four, depending on the angle at which the rollers are mounted, so these are rollers are mounted on the wheels, what can happen is that we have a resultant force in a particular direction. For example, if I rotate it in the clockwise direction, the force is going to be this side. If I rotate in the anti-clockwise direction, the force will be this side now. Okay, so by manipulating the direction of the force, I can make the robot move in a particular direction. For example, such robots can also go like this. Okay, they can go forward, they can turn, and they can also go sideways, simply by manipulating the direction of the forces on those wheels. Okay, so such robots are called omnidirectional mobile robots. Whereas this one here, which is a differential drive one, yeah. So this is a non-holonomic mobile robot in which we have two side wheels and a caster wheel in front. Okay, now in this what would happen here is that depending on the direction of rotation of the wheels, okay, this robot can go forward, it can go backward, and it can turn about its axis also, but it cannot go sideways. Okay, sideways motion is not possible. Now such a robot is a non-holonomic robot. Okay, now there are many examples of such systems in the real world. For example, kinematic constraints. Now what do these kinematic constraints do? These kinematic constraints will restrict some of the motions. Okay, now what about configurations? Okay, for example, let's take the case of this parallel parking of this car. Okay, so I have a car. This car wants to go and park here like this. Okay, now is it possible for the car to go and park like that? Okay, now in one shot it can't go like that, obvious, but can it have a number of maneuvers by which the car can actually maybe going front, turning, okay, or going front and back and turning? It can go and park. As you can see here, it is able to park like that. Okay, so basically it turned, went like this, okay, then again turned, went like this, and then parked like this. Okay, now this is basically what is called parallel parking. Now there are two questions here being asked. Number one is, because this car has a kinematic constraint which does not allow the car to go sideways, okay, now will it restrict some of the motions? Yes, for example, the car cannot go sideways. Okay, so it is restricting some of the motions of the car. But what about configurations? Okay, now the question is interesting because although the car cannot go sideways, can it go and park like this? Is this configuration possible? Okay, and that is what comes under the study of what we call controllability. Okay, we'll see that although there are kinematic constraints, but the system is fully controllable. That means it is possible to go and obtain any configuration. May not be in one motion, but in a series of motions. That is interesting. Now, this is another example, fingertip rolling contact with friction. So you have the multi-finger hand, which is manipulating an object. Okay, is it possible that the motion of this object is constrained in some directions? Okay, are there kinematic constraints? And the second question, whether it is possible to obtain all configurations for this object. That means may not be in one shot, but is it possible to orient this object in any way you want? Okay, so the question is, there are kinematic constraints, yes. So some motions are restricted, yes, but the system is fully controllable. That means you can obtain any configuration you want. Some more examples. For example, here, underwater vehicle with two rear thrusters. So this is an underwater vehicle. So these are interesting examples that there are two thrusters here. There is one thruster here, another thruster here. So let's say this applies the force F1, this applies the force F2. Now, because there are two thrusters on the rear side, there is one here and one here. Okay, this cannot go sideways. Okay, some kinematic constraints are there. But is it fully controllable? That's an interesting question. Okay, that means although it cannot go sideways, can I go and park it here? That is almost like saying it is going sideways. So the answer is yes. It cannot go sideways, but I can have maneuvers by which I can, not with one maneuver, I can have a number of paths by which the robot can actually go and park on sideways. So it appears that it can go and park here. So this configuration is possible, although not in one shot. Okay. So in our path planning, we'll talk about these kind of problems, that what are the different paths it has to follow such that it can go park sideways. Now, this is another example, the tractor and trailer problem. And there is a problem, this is also a question of controllability. So in the previous case, let me just go back here. We can ask the question of how many control variables are there and what is the degrees of freedom of the system. Okay, for example, let's go one step back here. This car has an XY and a theta. Okay, that means there are 3 degrees of freedom. However, the control variables are only 2. So only 2 control variables are there. Okay, which are the control variables? The steering on the front and the wheel velocity and the rear. So there are only 2 control variables, but it has 3 degrees of freedom. So is it controllable? Can you control this 3 degrees of freedom having only 2 inputs? That is the question of controllability now. Similarly here, the input is only F1 and F2 because you have only 2 thrusters. But if you consider only planar motion, then this also has 3 degrees of freedom. It also has, it can go up and down. Yes, let's ignore that. But on this plane, it only has 3 degrees of freedom. So can you control 3 degrees of freedom having only 2 inputs? Now, tractor and trailer problem. I'm sure you have seen these tractors which carry trailers on the highways. So there's a tractor in front and there's a trailer at the back and it's pulling the trailer. Okay. Now, in this case, the tractor was parked here. Now, can it go and park here? Okay, so simply by looking at this problem, it's difficult to say. Okay, but from controllability point of view, we need to look at how many configuration variables are there and how many control variables are there. And is this system fully controllable? If it is fully controllable, that means you can go and park in any configuration. Not in one step, but in multiple steps, or by following multiple paths. Okay, so the question of controllability is very important here because the number of actuators or control inputs is less than the number of degrees of freedom of the system. This is an interesting problem. Now, if you want to make it more interesting, so I have a tractor, okay, which is pulling a trailer. Okay, and there's a trailer. You know, the trailer is connected with the pivot, and it is just connected there, and it has 2 wheels. Okay, so this is a tractor trailer problem as shown in the figure here. Now, suppose I connect one more here. Is this still controllable? Is it still possible for this to go and park somewhere? Suppose I connect one more. Okay, can I keep doing this and it will still be controllable? Or there is a limit by which, after which you say that you can't park it anywhere? Okay, so these are interesting questions. So this is the tractor trailer problem. Okay, now systems can be non-holonomic and they can be non-controllable. For example, in this particular case, this is the car and I want to park the car here. Okay, so this blue car is my initial point and this is my goal point. Okay, I want to park it there. Is it possible to park it there in one shot? Okay, in which case I am moving only forward. That means the car can go forward and it can turn at a particular angle. It cannot go backwards. Let's say I have a kinematic constraint, or we have a kinematic constraint there that the robot cannot go backwards. Okay, so in that case, is it possible to go? Okay, so again the car would have two variables, which is the wheel velocity and the steering angle phi, and it has 3 degrees of freedom. Okay, so is it still controllable, or this is not possible? Okay, now if it is possible, then what are the ways by which it can do that? In this particular case, it is not possible. Okay, simply by going forward, the car will not be able to park there. Whereas if the car goes forward and backwards, then it is possible to get into that position. Okay, so this is an interesting problem where simply by moving forward, it is not possible. But by moving forward and backward, it is possible to go and park in that position. Okay, so in this case, it is non-holonomic, but it is controllable. Okay, so how can it do that? For example, it can go like this and then can come backward like that. Okay, so that is one way by which it can go and park that way. So this is my so this is a case which is non-holonomic but is controllable because it can move forward and it can also go backwards. So it is possible to get to the final position. Now let's look a little bit into the dimensions of C-space and kinematic constraints. Now, two parameters x and y are enough to specify all the points of a robot that can only translate. This is something we have seen. Okay, so if a robot can only translate, then we need only x and y. Okay, and these two parameters make up the configuration space. So if I have a robot like this and I have r, then xy, if I tell you xy, the position xy, and I know what is r, the radius of the robot can only translate, then 2 is only enough. Okay, so these two parameters make up the configuration of the robot. So configuration space or C space is the space of all configurations of the robot, and the configuration is just a point in the C space. The robot is shrunk to a point. This is something we have done a few classes back, that the robot is here. The robot has a radius r. So what we basically do, we shrink the robot. So this gets shrunk, the work area gets shrunk by r, so it becomes smaller, and the robot becomes a point. Okay, that is what we have done a couple of classes earlier. The robot becomes a point. Then I do the planning for the point robot. So this is a point robot. Okay, now the C space looks like Cartesian space, okay, in this particular case, but they are different spaces. Now the degree of freedom of the system is the dimension of the configuration space. That is something we have seen earlier. Now 3 independent point robots have total of 6 degrees of freedom. Okay, so what we are trying to derive here, or the direction in which we are going, is that we are trying to see that what is this kinematic constraint and what are the different kind of kinematic constraints that are there. Okay, based on which we can classify a system as holonomic or non-holonomic. So 3 independent point robots. So we have 3 point robots. There are 3 of them, say 1, 2, and 3. Each one of them have 2 degrees of freedom. We have seen that in this particular case, only xy is required for a point which is translating. Okay, so here each of them have 2. So this is xy, this is x dashed, y dashed, and this is x double dashed, y double dashed. Okay, and they are independent, means they are not connected in any way. There is no connection between them. So the total degrees of freedom is 2 plus 2 plus 2, which is equal to 6. So there is a total of 6 degrees of freedom on this system. And there are no kinematic constraints between the point robots, that they are not connected in any way. Okay, So this is a particular case where the robots are independent, each has 2 degrees of freedom, and the total there are 6 degrees of freedom, okay, of the system. Now let us look at the case of a 2 degree of freedom serial arm robot. Now this is a serial arm robot. Let's say it is this is one arm and this is the other arm. Okay, two serial arm robots like this. So this is a revolute joint, one revolute joint here, one revolute joint here. So these are 2 degrees of freedom, 2R robot. Okay, this is fixed space, so this is fixed now. Now each of these links has 3 degrees of freedom. Okay, so each of this has 3 DOF, okay, that we know. So if I simply leave this object in space, okay, suppose it's just one link, okay, then each of these links, if they are not connected, so not connected links have 3 DOF each. Okay, not connected or no joints, right? So this object, if it's just a link, it has x, y, and it has theta. Okay. So there are 2 links. So there has 3 plus 3 is equal to 6 DOF now, if they are not connected. But the moment I make joints, what do these joints do? These joints put some kinematic constraints. What kind of kinematic constraints? For example, if this is my point A, joint A, this is my point B, joint B, and this is C. Then the moment I put this joint, what would happen? The distance between A and B gets fixed. Okay, why? Because I put a joint at A. Okay, so this B can only rotate, the distance between A and B is now fixed. Okay, so this distance gets fixed now. Okay. That means how many constraints have been put? So the distance between A and B means fixed, the X and the Y are fixed. That means there are 2 constraints. Okay, so the distance XA or XP minus XA root over squared, this is 1. Okay, the distance in the X direction, distance in X direction and Y direction get fixed. Gets fixed, right? So there are how many constraints? So 2 kinematic constraints have been put. Now what about B and C? This is A and B. Now B and C are also constrained by 2 kinematic constraints. That means the distance in X and Y directions. So there are 2 kinematic constraints there. So kinematic constraints are 2, kinematic constraints are 2. That means what is happening here is we have 6 degrees of freedom if there is no joint. The moment I put these joints, we get 6 minus 2 minus 2, which is equal to 2 degrees of freedom. And that's how we have 2 degrees of freedom system. So when I said 2 DOF 2R, this 2 degrees of freedom comes from here. Each of this, if it is not connected, it has 3 degrees of freedom each of the links. Consider this to be planar. Okay, this is a planar example. Okay, and the moment I put the joints, the distance between the joints gets fixed now. So that means there are 2 constraints. So it is 6 minus 4, which is equal to 6 minus 4 equal to 2 degrees of freedom. Okay, now this constraints that I have put is a distance constraint. Okay, that means the distance between A and B is fixed now. Okay, so a scalar constraint of the form FQT, where f is a smooth function with non-zero derivative, is called a holonomic equality constraint. Okay, so these position constraints that have been put because of this joint, this is a position. It is basically putting a constraint on the position of A and B, right? So a scalar constraint of the form FQ t is equal to 0, where f is a smooth function with non-zero derivative, is called a non-holonomic equality constraint. So it's a non-holonomic equality constraint. And each independent holonomic constraint, sorry, this is a holonomic equality constraint. Okay, so a scalar constraint of the form FQT equal to 0, where f is a smooth function with non-zero derivative, is called a holonomic equality constraint. And each linearly independent holonomic constraint reduces the dimension of the system's configuration space by 1. In the previous case, it was 6 degrees of freedom, and each of the links had two kinematic constraints. So it was -2 and it was -2 kinematic constraints, and it became 2 degrees of freedom. Okay. So each linearly independent holonomic constraint reduces the dimension of the system's configuration space by 1. So if there are 4 constraints, it becomes 6 minus 4. So we have only 2 constraints left. So holonomic constraints are related to the position of the system. In the previous case, if you remember, we talked about the position of A and B. The distance between A and B are basically position constraints. Okay. Now, holonomic constraints do not change the path planning problem. Please note, this is very important. The moment you have a holonomic constraint, it doesn't change the path planning problem. Okay. So whatever we have talked about, the path planning of this serial arm manipulator. Okay. For example, obstacle avoidance, going to C space, and then finding the path. So that problem still remains the same. It does not change the path planning problem. Okay, so holonomic constraints do not affect the path planning problem at all. Now, what about differential drive robots that can translate and rotate? Okay, for example, this robot that we see here, this is a differential drive robot that can translate and rotate. Okay, now how is this robot going to move? It has a velocity there. Okay, let's call it a velocity v. Okay, velocity of the wheel, and this will mean that it has a velocity of that center point p, and there's a turning angle phi. Okay, so basically what we have here is that this has 3 degrees of freedom. This is something we have seen, x, y, and theta. Theta is the angle that the x of the robot is making with the global x dashed. Okay, now in this particular case, we know that the robot cannot go sideways. Okay, now, so are there constraints that prevent motions in some directions? Okay, and those constraints are called holonomic constraints. Now, if you look at this, basically, we can see that when the car is rotating, when it is taking a turn, it is taking a turn like this. Okay, it is taking a turn. The velocity here has to remain tangential at that point. Okay, and because of which what would happen is a kinematic constraint would be imposed on the car. And because of this kinematic constraint, which is a velocity constraint, this cannot go sideways. So here we have constraints that prevent motion in some directions, and these are velocity constraints. Okay, these velocity constraints are called non-holonomic constraints. Okay, now what is the velocity constraint that has been imposed? The velocity constraint that has been imposed is that when we are taking a turn, okay, this velocity has, the velocity of the car of that point P has to be tangential to that curve at that point. So if I go to the next point here, it will be tangential there. Okay, so if I come to a point here, it will be tangential there. Okay, so when the car is moving at every instant, its velocity is tangential to the curve at that point, and that is causing a velocity constraint now, because the velocity is being constrained in that direction. Okay, I'll come and explain a little bit more as we go along. Okay, now this is a velocity constraint, and this is a non-holonomic constraint. And non-holonomic constraints ensure that this robot cannot move sideways because its velocity is constrained. Okay, now so a non-holonomic constraints are velocity constraints. We just saw that the velocity is forced to move in a direction which is tangential to the curve at every point. They do not reduce the dimension of the system's configuration space. Okay, so for example, in the previous case, it was a 3 degree of freedom system, and we have one velocity constraint. Okay, but it doesn't reduce the reduce the dimension of the system's configuration space. Okay, now a non-integrable scalar constraint of the form f(q) dot t is equal to 0 is called a non-holonomic equality constraint. Okay, so it is written this way. So in the previous case, if you note, this was f of qt, where q is position. This is position. Okay, x, y basically. Okay. Whereas in this case, in the second case, what we are seeing is that there's a q dot, so it's x dot, y dot. So there is a velocity constraint now. Okay, because the velocity of the robot is constrained to move in a direction which is tangential at every point on that curve. So it's a velocity constraint, hence it is x dot, y dot. Okay, or we can say dx, dy. Okay, so This type of a constraint is called non-harmonic equality constraint. Now, that is one. The second, this is a non-integrable scalar constraint. If it was integrable, you could integrate it and it would become a position constraint. Okay, so it will become holonomic. So one of the conditions for this to be a non-holonomic constraint is that it should be non-integrable scalar constraint. Okay, that means you are not able to integrate this. And the non-holonomic constraints do not reduce the dimension of the system's configuration space. These are some things that we have to remember as we go along. So we have seen two kinds of constraints: holonomic, which depend on position; non-holonomic, which depend on velocity. Okay. Now, issues with non-holonomic constraints, first of all, is that how can we be sure that kinematic constraints is a non-holonomic constraint? If it is integrable, it can be reduced to holonomic constraint. Okay, so the first thing is that we have to be sure that it's a non-holonomic constraint. Now, does non-holonomic constraints restrict the configurations reachable from a given configuration? Now, using Lie brackets, we will show that non-holonomic constraints do not affect the reachable configuration space, which basically means that the system is fully controllable. That means, suppose this is just an example. We have a car. I have a car which has 4 wheels. Now the car cannot go and cannot go sideways, right? It cannot go sideways because of this velocity constraint. But suppose I want to go and park it here. Is it still possible? That means, is every configuration achievable? So the theorem basically tells us that although we have a non-holonomic constraint, but these non-holonomic constraints do not affect the reachable configurations. Okay, using Lie brackets, we'll be able to show that non-holonomic constraints do not affect the reachable. That means it can actually go sideways also. It cannot go sideways, it can go and park sideways by using a number of maneuvers. Okay, so for example, it can use different maneuvers to go and park sideways. So if that is the case, then we need to build an effective planner that can plan the paths from a given configuration to other configurations. It cannot go sideways, okay, but then I plan a number of paths which will take me from one configuration to another configuration in such a way that all configurations are reachable. Okay. Now, degrees of freedom of robot or dimension of configuration space of a robot with drive and steering. So, how is a car controlled? So, let's look at this again here. This is a car. Okay, so these are 4 wheels. This wheel, let's say, has a turning. Okay, so this one can, sorry. Okay, and we have the global X, that's the global Y, and we have a local X and a local Y, which is given here. So that's my local X. This is X dashed, and that's Y dashed. Sorry, it has to be the center point. There is Y dashed. This is my point P. It has coordinates X and Y. Now, how is this car controlled? There is a wheel velocity which is omega, because of which there is a linear velocity which is V. Okay, this point P has a velocity V, and there is a turning angle which is there. So there is a turning. So let's say this is my angle phi. Okay, so input out degrees of freedom of a car are equal to 3, which is X, Y, and theta. Theta is the angle the x-axis is making. X dashed is making. So this is my angle theta. Okay, so it has 3 degrees of freedom. How are we controlling it? So trying to control it is by only with 2 inputs. One is V, the wheel velocity, and the other is my angle phi. So these are the 2 control inputs. Okay, so I'm controlling the car, the 3 degrees of freedom of the car, by using only 2 inputs now. So the question here is, can the car go and park anywhere? Okay, so are all in the configuration space, can the car go, are all the points in the space achievable for the car? Okay, that's what we are looking at here. Now, car with drive and steering. Now, there can be different kinds of, let me just, as we are talking about this, the other kind of robot that is there is this type of a robot. You can have a robot which is like this. This is joint, right? So we have a robot which is, again, it has velocity V, and it has a single, let's call this phi. Okay, here also it's v and phi. Okay, so this is a mobile robot which has a drive at the back and it has a steering angle in front. You can also have a robot which has this kind of robot where you have different drives, differential drives, and there's a caster wheel in front. Okay, so there is omega 1, omega 2. Now all of these are subjected to kinematic constraints. Okay, that means this robot cannot go sideways, this cannot go sideways, this car cannot go sideways. That means it has a velocity constraint. Okay, now let us look at what this velocity constraint looks like. So car with drive and steering. So this is, let's look at this carefully. So this is the car and this is the point, let's call this point P. I had talked about this point P. So let me write it as P. The point is the center point between the two wheels, which is here. Okay. Now phi is the steering angle. This is steering angle, and theta is the angle it makes with the x-axis. The local x-axis of the car is making with the global x. Okay, that is my angle theta. Now phi, when the car is rotating, there is an instantaneous center of rotation which is here. So this is my IC, instantaneous center of rotation. So the car is rotating about that point. Now let us say that the car is taking a turn like this. The car is taking a turn. Car is taking a turn like that. Now at this point, when the car is taking a turn, the velocity vector is going to be in this direction. Okay, it is always, the direction is always along the y-axis of the car, right, in the front direction. Now if that is my v, then dx by dt is equal to v cos theta. Okay, so I can break it up into two parts. I can break v into two parts. One will be dx by dt, which is v cos theta, and dy by dt is v sin theta. Okay, and when I divide this by this, I divide this, what would happen? dt will cancel, and I have dx sin theta minus dy cos theta is equal to 0. Okay, so if I take, we have the direction of v. I hope you understand this. Now when I take the v cos theta, okay, I get the velocity in the x direction, and v sin theta is the velocity in the incremental velocity in the y direction. Okay, now what we get is, this is what we call my kinematic constraint. Or velocity constraint here now. Now this velocity constraint is the one that ensures that the robot cannot go sideways. Why? Because at every point on that curve, the velocity has to be tangential to that curve. Okay, and that is, and what is the constraint? It is dx sin theta minus dy cos theta, and d theta by dt is equal to v by l tan phi. Okay, now tan phi is less than, this is my maximum steering angle. So every car can steer only by a particular angle, right? A car cannot, the front steering wheel cannot become 90 degrees, right? So there is a limit on that, how much you can steer, and that is my maximum steering angle. Now the configuration space is 3 dimensions, which is x, y, and phi, but the control space is 2 dimensions. You have v and phi, which is my drive and my steering, and the velocity is constrained this way. V is equal to square root of dx by dt squared plus dy by dt squared. Okay, so I hope you understand where this constraint came from. So this is the kinematic constraint that the car is subjected to, because the velocity has to be in that direction. Okay, and it's very easy to derive that if you take the components in the x and y direction, you get equation, this equation and this equation. You divide both of them, you get the kinematic constraint. Okay, now this is the same car. What we are saying that a robot is non-holonomic if its motion is constrained by a non-integrable constraint of the form f q q, and in this particular case, this is the non-holonomic constraint. Okay, and you can see it as dx sin theta minus dy cos theta is equal to 0, and dx and dy are velocity. Okay, so it is x dot and y dot. Okay, so basically what we are saying is the robot is non-holonomic if its motion is constrained by a non-integrable equation of the form this, and this equation is this one. So we are seeing that a car is subjected to a single non-holonomic constraint. So a car is subjected to a single non-holonomic constraint. of this form. It is non-holonomic constraint. Okay, so it is going to, this non-holonomic constraint will cause the car not to be able to move in some directions. Okay, so the car cannot go sideways, but it is fully controllable. That means it can go and park, it can achieve every configuration. Now, what does this equation actually tell us? First of all, is that it is a non-holonomic constraint. Okay, so it is a velocity constraint, so it is non-holonomic constraint. Okay, now what does this equation actually tell us? That there are some directions in which we cannot move. I said the car cannot move sideways, but how can you say that in terms of the equation? Okay, now in this equation, if theta is equal to 0, so theta being equal to 0 means if this is my global axis. Okay, so if theta is equal to 0, it basically means the car is like this. Okay, theta is equal to 0 means the car is this side now. That is the car now. Okay, that is the car theta equal to 0. Okay, so the x-axis is also in this direction, now the car's x-axis. Okay, that's x equal to 0. Now, if theta is equal to 0, then velocity in y direction is equal to 0. So, in this equation, if I put theta equal to 0, then what will happen? This will become 0. Okay, then what we are going to get is y dot cos theta is equal to 0. That means y dot is equal to 0. That means the velocity in y direction is equal to 0. What is the velocity in y direction? It is this side. It is 0, which means if it is fully, when theta is equal to 0, y dot is equal to 0. That's what it is saying. That means it can't go sideways. Whereas on the other hand, if I draw it again here, let me draw it again here. If the car is facing this side now, okay, the car is facing this side, which means that the local axis of the car is of this side, this and this. Okay, in that case, sorry, this and this. So x-axis, that's my y-axis. So in this particular case, what is theta? Theta is equal to 90 degrees. Okay, this is my x and that's my y. So theta is equal to 90 in the second case. Now, if theta is equal to 90, then what happens is x dot sine theta becomes equal to 0 because cos theta is 0. So cos theta is equal to 0. Now, this means that x dot is equal to 0 now. Okay, so which basically ensures that the velocity in the y direction is 0 now. Sorry, the velocity in the x direction is 0. So it means it can't go sideways, it cannot go this way now. Okay, so what we are seeing is that when theta is equal to 0, it cannot go in the y direction. When theta is equal to, when theta is equal to 90, theta is equal to, please note the correction, theta is equal to 90, then this is equal to 0. So when theta is equal to 90 degrees, then sine theta x dot into sine theta is equal to 0 and x dot is equal to 0. Okay, this is 90, so x dot is equal to 0. Okay, please note that. Okay, so this too basically tells us that we have this constraint, and what this constraint does, it ensures that the car cannot go sideways. Okay, now let us see this in a little bit more detail. I'm going a little slow because you need to understand this very clearly. So we have my turn, which is like this. Okay, that is taking a curve. At that point, this one point P, the vector is in this direction. Okay, now we get one equation from that, dx sine theta minus dy cos theta. We get another one which is here. Now in terms of the car which is rotating about this instantaneous center of rotation, IC is there, which is rotating about the instantaneous center at that instant. Okay, in that case, if this is my rho, instantaneous center of rotation, if this is the radius, then 1 by rho minimum is equal to 1 by L tan phi max. What is L? L is the distance between these two wheels, and phi max is the maximum turning radius. Okay, so this is phi max. So it is constrained by this equation, x dot squared plus y dot squared minus rho min squared into theta dot squared is greater than or equal to 0. Okay, so how do we get that from? This is my rho. Okay, that is my rho, instantaneous center of rotation. Okay, so the radius of rotation is 1 by rho, which is equal to 1 by L tan of phi max. Okay, and from that we get this equation, that x dot squared plus y dot squared minus rho squared, rho min squared into theta dot squared is less than is greater than or equal to 0. Okay, now this ensures that there is a lower bounded turning radius of the car, and this condition has to be satisfied. Okay, now what does this mean? Now this basically means something very interesting. Please look at this very carefully. So we have a radius here. This car is rotating. This is the velocity vector which is in that direction. Okay, now this is my x-axis, this is my x-axis, that's my y-axis. So I'm drawing my x-axis, y-axis here. So on the ground, this is my curve that the car is taking. Okay, this is the curve that it is taking. Now at that point, this is the point. Okay, this is my theta x. Now at that theta, okay, the vector is pointing in which direction? The vector is pointing in this direction. It's tangential to the curve there. At that particular theta, for a particular theta, this is my x-axis, y-axis, and this is my theta axis. So at that point on theta, the vector is in this direction now. Okay, that's my dx dy. Okay, that means at every point here, there is going to be a vector. Okay, now for different thetas, there can be different thetas of the car. The car could be pointing in different directions. For example, this is another curve. Okay, in this particular case, the car is pointing this side now. Okay, let me draw it with some other color. This is blue. Let me use red color. So at this instant, when the car is like this, the car is like this. Okay, the car is like this. Okay, what would happen? The vector is now, the curve is like this now. So the vector is this side now. Okay, now through this point P, there can be different curves, right? But for each of those curves, the vector has to, the velocity vector will be tangential at that point. Okay, so what it basically means is that for different thetas, when the car is turning, this theta is changing, right? This theta and that theta is different. So for different values of the theta here, there will be different vectors which are going to be there. But these vectors will have to lie on this plane. Okay, this plane, which is passing at this point. So all the vectors will have to lie on that plane. Okay, and this is also called the tangent plane. Okay, now if that is the case and there is a turning radius, we have seen that it is constrained to move, it is constrained to move in a particular direction. It is constrained by this equation. Why? Because there is a turning radius and there is a turning radius here and there is a turning radius of the wheel, of the steering wheel. Okay, phi max and rho is there, which means that this condition has to be satisfied. Okay, which basically means that, just coming back and explaining this again, okay, at this particular instant we have a curve like this, and let's say I have a curve like this, and it's tangential there. So this curve is on my xy plane, this is my xy plane. Okay, so for this point, which is the point P, okay, so for the point P we have a curve for a particular theta, whatever was the theta here. So in this case, let's say my theta was this much. So for that particular theta at that point, this is my theta axis, my tangent was in this direction. Okay, but for different thetas, there can be different curves. Okay, there can be different curves at that point. But for each of those curves at that point, the tangent will be in different directions. But they must all lie on this plane. And this plane is basically called the tangent plane. Okay, so this plane is basically what we call the tangent plane. Okay, so please think of this carefully, that why must the tangents lie on that plane? Now, if the tangents are lying on this plane and the tangents are bounded by that equation, okay, x dot plus y dot squared minus rho squared phi min squared greater than or equal to 0, if they are bounded by this equation, then it basically means that all the tangents have to lie inside this cone. Okay, so all the tangents have to lie inside this cone. Okay, this is what it means, that the tangent will lie on this plane called the tangent plane, and because they are bounded, that means the car cannot turn. This has a bound. Okay, the turning radius has a bound, and this steering angle has a bound. Okay. Now that bound will ensure that the tangents will lie inside this cone because it has to satisfy this equation. Okay. So this basically gives us the idea of a tangent plane and also the cone inside which the tangents must lie always. Okay. Now we need to think of this a little bit more before we proceed. So let's talk about this tangent space and tangent bundle. Let's think of it a little bit differently. So suppose I have a sphere. Okay, I have a sphere. Okay. Now on this sphere, I have a smooth curve. Let's say M is a smooth curve. Okay, so I have a smooth curve which is like this. Okay, that's a smooth curve. Okay. Now at this instant, at this point on the curve, I have a tangent. Okay. So V is a tangent, dx by ds. So x is tangent at x naught. At this point, x naught is a tangent. Now we can have different curves which are going through that point. I can have different curves, right? So from here, I can have, let me draw another curve here which is going like this. I can draw another curve which is going. These are all curves going through that point only. Okay. So these are all curves which are going through this point, the same point x naught. Now in each of those curves, there is going to be a tangent. And the tangents will be in different directions because the curves are in different directions. Okay. Now all of this tangents will lie on a space. Okay, so these are all tangents, if you can imagine. And this is basically called my tangent space. This is called my tangent space. So we can say that all the tangents live or have to be on the tangent space. Okay, which is this one. So this is my tangent space. Okay. Now each of these tangent spaces is basically a vector field because it has tangents in all directions. All the tangents which are coming at that point are contained in this itself. Okay. Now at different points, there will be different tangent spaces on the sphere. For example, if I take some other point here, we talked about x naught only. Suppose I take some other point here now. I take this point which is somewhere else. Okay. It's on the sphere. Now these are all curves which are going through this point now. Now here also there will be tangents. Okay. Now there is going to be a vector field here also. So all those tangents will lie in there. Okay. So this is another tangent space. So sum of all these tangent spaces basically make up the tangent bundle. Okay. So this is the idea of a tangent space, where the tangents lie on that point, or all the tangents at the point lie. Okay. And sum of all the tangent spaces, make up what we call the tangent bundle. Okay. So sum of all tangent spaces make up what we call the tangent bundle. Okay. So this is exactly same as what we have just seen here, but this is maybe a little bit easier to understand what is a tangent space and what is a tangent bundle. Okay. Now this kinematic constraint is the one that is causing all this, because it is enforcing that the velocity of the car has to be in a direction which is tangential to the curve at that point. Okay, and hence it has to lie in the tangent space, and sum of all these tangent spaces make up the tangent bundle. Okay. Now any kinematic constraint of the form that is linear in Q can be written as this. Okay. So G of Q into Q dot can be written in the form W into WQ. Okay, where Q is basically XY. Okay, these are coordinates. XY into Q dot is equal to 0. Okay, that means a kinematic constraint of this form can be written in this form. Okay, where Q is a smooth function of where W is a smooth function of Q. Let's take the example here. So we are looking at this where the kinematic constraint, which is this one, is written in the form W Q into Q dot is equal to 0. Okay, Q are X and Y now. These are the X and Y's. So what is W here? So X dot and Y dot is my Q. So what is W? W is sine and cos. Okay, so these are smooth functions of Q. So what we are seeing is that I can write the kinematic constraints of this form in the form w into q dot is equal to 0. And any given configuration of robot velocity can be expressed as a linear combination of x1, x2, x3, which are set of independent vector fields in spanning delta. Let xy be a set of independent vector fields in delta. Okay, what we are saying is that you can have x dot, y dot, which are basically directions, velocities in x direction, y direction. Now, by combining all these velocities in different directions, you can generate, okay, this is what it is telling us, that any given configuration of the robot velocities can be expressed as a linear combination of x1, x2, x3, which are the set of independent vector fields spanning delta. Okay, and if xy be a set of independent vector fields in delta, velocities in the x direction and y direction, then what happens is you can move, the system becomes fully controllable, and you can park, or rather what this basically means is that the system is fully controllable. Now, a non-harmonic constraint of this form can be written in this form as w into q dot is equal to 0, and because of this, the system is fully controllable. Why? Because at any given configuration, the robot velocity can be expressed as a linear configuration of x1, x2, x3, which are a set of independent vector fields spanning delta. What this basically means is that in this particular case, the robot can only go this side and front, okay, but not backwards. In this case, the system is not controllable. But in this particular case, the robot can go in x direction and it can go back also. Okay, for example, it goes like this and then goes like this and parks. Now the system is fully controllable. This is non-harmonic but controllable. Now what we are trying to see is how do you park sideways, or how do you move sideways? Okay, that is something which we'll be seeing in the next class by using Lie algebra, that how can the system be moved sideways. Stop today with this, just to maybe just to keep you thinking, is if you have, just as a small homework, okay, can you think of this unicycle? You might have seen this unicycle where there is one wheel, the person can pedal and turn at a point. So this can move forward, this can move forward, and it can spin at a point. So with this, if this is my top view, I want to make it go here and park like this, sideways. Now this cannot go sideways, right? But using a number of x dots and y dots, motions in the two directions, can I make it go and park sideways? Okay, for example, okay, I go straight, this is going straight, then I turn, I rotate at a point, can spin at a point, right? Then I come back, I come back here, so it is like this. Okay, so go straight, turn, then back, and then turn again, turn this side again, turn this side again, and it has parked like this. Okay, so there are 4 steps. Go straight, turn, go back, turn, and in these 4 steps, it is going and parking sideways. So this configuration is controllable, because although this single wheel cannot go sideways, we are seeing that this wheel has actually gone sideways and parked there. Not in 1 step, but in 4 steps. Okay, this is the meaning of having different combinations of x dot and y dot, okay, to define the vector field. Okay, so please think about this, and in the next class we'll be seeing this in more detail, especially in terms of Lie algebra, that how is this system controllable, although it does appear that because of the kinematic constraint, the system cannot achieve all configurations. In the next class we'll be talking about Lie algebra, where we have to actually prove, and after proving that the system is controllable, we have to derive or design path planning algorithms which can take a robot and make it park anywhere, including the tractor trailer problem, in which case the algorithm should automatically be able to park the car wherever you want it to park. Okay, and if the system is fully controllable, then you should be able to park anywhere. Okay, so we'll stop here today. Thank you.